This is TMUA 2021, Paper 1, Question 14. We want to work out the number of distinct solutions to this equation. X plus 1 times 3 minus x is equal to 2 lots of 1 minus cos pi x. How might we do this? Well, we could try solving it algebraically, but this is going to be hard because we have a polynomial on the left-hand side and a trigonometric function on the right. So how else might we do this? Well, you consider graphically, and then the number of solutions would be the number of intersections between the graph of this curve and the graph of this curve. So let's try and sketch both of these two graphs. So starting with x plus 1, 3 minus x, this is a negative quadratic which has roots at minus 1 and 3. So sketching that should give us something which looks like this. What other features do we know about this? Well, let's try and work out the coordinates of this maximum. And this is when the derivative of this is going to be 0. So that's when minus 2x plus 2 is equal to 0, which gives us x equals 1. And plugging that in gives us a y coordinate of minus 1 plus 2 plus 3, which is 4. So our maximum is going to be at 1, 4. What else do we know? We know the y-intercept is going to be 3. So this is going to be the sketch of our graph. How does 2 times 1 minus cos pi x look like? Well, first, you can see this is going to be a transformation of cos x. And let's see if we can draw cos pi x first. Well, what is this? Well, this is precisely a scaling by 1 over pi in the x direction, or like a shrinking by a factor of pi. So what happens to the period of cos when under this transformation? Well, the period is now 2 instead of 2 pi. So how does that look like on the sketch? Well, if you draw it now, this is a cos graph with max at 1 and negative 1, and then we need to know where these roots are and these 1s are, the x values. Because it's been shrunk by pi, these values will be precisely at a half, 1, this will be 1 and a half, this max is going to be at 2, and so on. So we can just literally divide all our known roots by pi. Okay, so now how do we get cos pi x, 2 times 1 minus cos pi x from cos pi x? Well, this is a series of graph transformations. So let's first go inside and out. So that's the way we do these transformations. So we have cos pi x, then we have a minus 1. So what does that mean? That means we flip our graph in the x-axis. So how does that look like? So if we take our original graph and we flip it in the x-axis, this point 1 goes to minus 1, but the zeros stay where they are, and everything else flips. So it becomes something like this. What do we do after this? Well, moving outwards, we see a plus 1 here. So that means we translate our graph up by 1. So doing that, we get something like this red curve. And now note, our maximum is now at 2, and the minimum is 0. And what's the final step of this transformation? Well, we have this times 2 on the outside, so that means we stretch everything vertically times 2. So we're going to get a graph which looks like this. And where are these maximums going to be at? Well, previously the max was at 2, so we multiply by 2, it's going to give us the maxes at 4. And then remember, because in all of these transformations we're only moving stuff vertically, so all these maxes will still remain with x coordinate 1 and x coordinate minus 1. Okay, so now we want to draw both of these two graphs together. So let's try and overlay them on top of each other. So cleaning it up, let's first draw the graph of 2 times 1 minus cos pi x. And we know that the roots are going to be here. And we also know that the maximum coordinate is going to be at 1, 4. Well, what do you notice about this? Well, this is precisely the same coordinate as the maximum of our quadratic. So when we overlay this graph, how would it look like? So it's precisely going to be, this point here is going to match up with this point. So we're going to have something that looks like this. And remember, and then now all we have to do is count up the number of roots. And so we have 1 here, 1 here, 1 here. That gives us 3. Are there any more? Well, no, because outside of minus 1, 3, our blue curve is going to be below the x-axis, but our green curve is positive for all values of x. So we have 3 curves here, which means the answer should be B. You may be wondering, why does the graph do this when the blue curve goes over, and why does it not intersect our cos graph at 2 different points before it reaches the maximum? So what is the difference between these two graphs? Well, in this first case, the cos graph drops quicker than the blue curve, so it's got its derivative is decreasing at a quicker rate than the blue curve, and in this case it's vice versa. So to investigate which case our graphs are in, we should investigate our second derivatives. So we're in this case precisely when the magnitude of the second derivative of our green curve, 2 times 1 minus cos pi x, is strictly bigger than the magnitude of the second derivative of our blue curve. So to determine this, let's create a table. So we have a table for f of x, the first derivative, the second derivative, and second derivative near 1, because that's where we're evaluating our thing at. And blue is going to be our parabola, and green is going to be our cos graph. So filling in the first column, we get this, which we already know. Then the first derivative, differentiating this, you get minus 2x plus 2. And then differentiating this, you get 2 pi times sine by x. Differentiating once more gives us minus 2 and 2 pi squared cos pi x. And then evaluating both of these things at 1, give us that we get minus 2 and minus 2 pi squared. So what do you notice about this? Well, you see exactly that the magnitude of minus 2 pi squared is bigger than minus 2. So which means the second derivative of our trigonometric graph is bigger, the magnitude is bigger than our parabola. And so it's more negative, which means it's going to drop quicker after 1 than the blue curve, which means it won't intersect again, which is why we only have one meeting point here. This is why the answer is B.